Alright, hello. So, good morning, good evening, good afternoon, whenever you're watching this, etc., etc. This is this is part 2 of lecture 6 of ENGR 2302 Engineering Dynamics. Continuing right where we left off. It's another late recording session, doing a makeup makeup recording for the upcoming Thursday class. Oh, did not mean to do that. Okay, and let's begin. So I'm going to continue right where we left off. And now I'm going to talk about the principle of work and energy. Principle of work and energy. Of work and energy. Work and energy here. So I'm going to draw another path here. And let's see. Another path in purple, because I seem to like purple for object paths. And it could be circular, but it doesn't have to be circular. It can be any path you like. And this time I'm going to actually draw a mass. So this time I will actually consider what happens when this thing has some mass to it. Well, actually, we looked at that, or we already looked at one example with mass, which was gravity. But let's say this thing has a mass m, and it's going to move from position 1. So this is going to be position perhaps A at any given time, A, and then A1 and A2 towards the end of the path, or at least the part of the path that we're looking at. It could easily continue beyond where we're drawing here, but this is just a very generic exploration. So if we remember, there's going to be the force doesn't necessarily have to be right along the path of the object. In fact, it may not. It may often not. More often than not, it will not be. So let's say we have the force F here. But let us break this down a bit more into components. So there would be a F tangential, Ft. So Ft for F tangential. And let's say, what do we want to call that? Let's call that Fn for F centripetal or F normal. Fn for F normal, the normal vector, the normal force. Well, it's not. I got to be very careful with that. When I say normal force, I'm usually only talking about when I say Fn or normal force, usually I'm only talking about contact forces between bodies. This would simply be the normal, or the component of the force that is normal to the path of the object. But anyway, so we know that only the Ft is going to do any work on the body. We know this already. We've seen this previously. And the angle between this, the force, and the path of the object at a point would be alpha, angle alpha here. Now, let's say I want to look at this here. So consider a particle of mass m, acted upon by force F. Acted upon by force F. Vector, so talking very generic right now. But the tangential component of this, of course, is going to be mass times the tangential acceleration, which is what we've seen in the previous chapter, or m dv dt. The tangential force is what produces a change in velocity. Is what produces a change in velocity, or a change in the speed anyway, I should say. Maybe not. I want to be careful with that. Even this Fn will produce a change in velocity, but it will produce a change in the direction of velocity. It won't change the magnitude of the velocity. So the only thing that's going to change the magnitude or the speed for this v, this non-vector v, will be the tangential component of the force. And then this is going to be equal to m dv ds. If I do an integration, so I adjust the integration here. So if I do a little change of variables, just basically multiplying by ds over ds. So imagine multiplying by ds over ds. So I could actually, if I wanted to, multiply by, I can always multiply by 1 if I want. There's no reason I can't. And ds over ds is just a form of 1. So if I multiply by that, well, and rearrange things a bit, I can get this. M dv ds times ds dt. Okay, so what does that do for us? Well, let's find out. Well, let's see. ds dt, we have a word for that. That's just velocity, or speed in this case, mv dv ds. Or I could also say ft ds is equal to mv dv. mv dv. Maybe we're getting somewhere. Maybe, we'll see. So now let's take this expression and now integrate from A1 to A2. Let's integrate from A1 to A2. So I would get the integral from A1 to A2. Actually, that would be, so let me say S1 to S2 for now, because those would just be the actual displacement values. I haven't drawn the S, it's integrating from A1 to A2, but there would be actually corresponding coordinates, S1 and S2. I just didn't bother drawing all those out, because as we've seen, these diagrams can get quite involved. So this would be ft ds is equal to m, we'll pull the m out here, times the integral from v1 to v2 of v dv, which will then produce 1/2 the integral mv2 squared minus 1/2 mv1 squared. And this, though, what do we have here? The integral of force, of tangential force, ds, from the two positions is just going to be u1 to 2. And maybe I misdescribed this earlier when I said what we're going to use for t. T in particular, I think in the earlier video I said it to be any other energy, but I think T in particular we're going to use a little more precise form. T we're going to refer specifically to kinetic energy. So T2 minus T1. Capital T is going to be, so lowercase t is time or tangential component of its subscript. Capital T is going to be kinetic energy. So in other words, T is 1/2 mv squared, or our old friend kinetic energy. So we can see via basic integration that the u from 1 to 2, the work from 1 to 2, will be equal to the change in kinetic energy. Our old friend kinetic energy. So then here, again, I can describe this again. The work of force F, assuming there are no other non-conservative forces acting on the body. If this is the only force acting on the body, the work of force F is equal to the change in the kinetic energy of the particle. The energy has to go somewhere, and if there are no other forces acting on the body, the only place that energy can go is in kinetic energy, is equal to the change in kinetic energy of the body. And then the units of work are going to be the same as force. Of work are the same, or sorry, of kinetic energy are the same. Of work and kinetic energy are the same. And kinetic energy are the same. Are, of course, the same. So T, kinetic energy, 1/2 mv squared, which is equal to the units of kilograms for, if we're using metric units, kilograms times meter per second quantity squared, or kilogram meter squared per second squared, or if I were to take out one of these meters, kilogram, let's say I pull out one of these, kilogram meter per second squared, just rearrange this a bit, times meters. Oh, a kilogram meters per second, that's just a Newton. So that's just going to be Newton meters, or simply 1 joule. And we could do the same thing for English units if we want. They would have, if we're doing kinetic energy in English units, it also will have units of foot-pounds, just like work does. Okay, so let us look at how we might work with some of these things. So again, the basic idea of the work energy equation, or the work kinetic energy, principles of work and energy, is, here's the basic idea. If there are no non-conservative forces acting on a body, then U from 1 to 2 will be equal to T2 minus T1. This is the basic idea of work and kinetic energy. And this is ignoring this is saying the work done by one single force. Now, in more advanced forms, we will also deal with gravitational potential energy, but that's really just the work of another force, the work of weight, or the work of gravity. But anyway. So let us look at some further applications of this. So let's consider this. Let's consider an example. I'm going to look at a pendulum. Applications of principle and work and energy. Of the principle of work and energy. Of work and energy. So let's see here. And let's look here. So we've done problems like this in the past, and we've had to do, if you're doing this via force balance, you would have to do a fairly complex integration. Well, not terribly complex, but say you have an origin here and a bob. I'll do different colors perhaps. We have a pendulum on a pendulum bob, or a pendulum bob on a string, whatever you want to call it. So it's going to have a path, nice circular path like that, if I can manage to draw a circle. And then let me draw a few points. So this would be a generic A, just some random position A. This would be the initial position, A1, and this would be the final position, A2. But all of these would have the same length L. L, L, L. I can't draw circles. Okay. Anyway, let's look at this. So let me draw a free body diagram of this. The weight, I'll actually draw kind of like this. Actually, no, I don't want to do that because that's just a point label. So I just have my pendulum bob at some point A. The path of the object is like so, here. And then my force will be perpendicular to this path. My centripetal force, my tension force. So I have some force. Maybe I could call this P, a pulling force. And then I have weight W pulling down, capital W. So, again, some label here. Let me label something. the bob is released from rest at A1. And let us analyze what happens to this. Is released from rest at A1. And maybe determine velocity at A2. And we'll assume the string is massless, etc., etc. And we want to do this, use principle of work and energy. And I think I'll work through this on the next slide. Of work and energy. Okay, so again, the force P acts normal to the path and does no work, so we don't need to worry about that one. And does no work. So then, let's look at, say, T1 plus U1 to 2 equals T2. So we don't need to worry about that. Now the initial kinetic energy is going to be 0 plus let's see, we already know that the thing here. Actually, let me make clear, I think I want to do something a little bit different. I want to modify this slightly, I think. It wasn't very clear, but I actually wanted this thing to be purely horizontal. So A1 is going to be perfectly horizontal. Just to make this a little bit clearer. This is also L. The nice thing about this, I have a pendulum here, bob here, bob here, bob here. The nice thing about this is that the change in height will be exactly equal to L when I do this. So I can simply replace the this with WL. See, again, I'm using the work equal to the force times the component of the force times the displacement in that direction. Well, the displacement in the vertical direction is just equal to L. Or, and then this is going to be equal to, let's say, where might this come from? WL. Let's see here. Yes, 1/2 mv squared. Now, I would like to, maybe before I do anything else, maybe I would do something a little bit different. What I could do is I could say, so this goes away, so I have WL equals 1/2 mv squared. Let me go and say, okay, WL equals 1/2. Now, 1/2, I know mass, okay, so I know weight equals mg. So therefore mass is equal to weight divided by g. So let me just replace that here. Oh, and this should be v2 squared to be clear that we're talking about the velocity at point 2. And then w divided by g times v2 squared. So all of these things are multiplied. And the w will simply cancel out. W will just cancel right out. And by a simple algebra from there, it's not too difficult to arrive at v2 is equal to the square root of 2gl. So this is an expression for the maximum velocity of a pendulum, an ideal pendulum. If you release it from, well, I guess it could have I shouldn't say the maximum velocity because it might have a slightly higher velocity. It would have a slightly higher velocity if you release it from a vertical position or a position above horizontal, I should say. But if this is the expression if released horizontally. Okay, now I don't care if you know much about pendulums. That's not the point of this exercise. Pendulums are fairly straightforward. It's not, working through the pendulum is not the real point of this. So let me sort of say the lessons here, the morals, whatever we want to call this, the takeaways. 1. In this case, velocity is found without determining expression for an acceleration and integrating. Without determining an expression for acceleration and integrating. We don't need to do that when we're using energy methods. Sometimes we can't use energy methods, but as long as we have no non-conservative forces, we can. And if I didn't mention it earlier, non-conservative forces means things like friction. It means things like air resistance, heat loss, things that are going to cause a loss of energy from your system. That's why they're non-conservative. So velocity is found without determining an expression for acceleration and integrating. And integrating. And another thing, too, all quantities are scalar, so they can just be added together directly. Are scalar and can thus be added directly. Can thus be directly added. And 3, another key to our energy method problem. Just to simplify things, we go and say, okay, forces which do no work are eliminated from our analysis. Are neglected in our, I shouldn't say neglected because we have considered them. I should say eliminated from our analysis. When we neglect something in an engineering problem, usually we're saying it's insignificant. In this case, the force P is not insignificant. It's just not doing any work compared to in relation to gravity. It's just not doing any work on the object. It's not insignificant. I shouldn't say I'm neglecting it, but I am eliminating it. I'm not neglecting it. Are eliminated from the analysis. Okay, let's see. Also, some more things. Other lessons, other takeaways. Notice, we did not know anything about the point, anything about the path from 1 to 2. I don't know. All I know is its final velocity. That's all I know. I know at the end, I know its height and its position and its velocity, and that's it. Or height and its velocity, that's it. So, the principle of work and energy cannot be applied to find the acceleration. So if you need the acceleration, if you need to know that, you can't use the principle of work and energy. And energy cannot be applied to finding an object's acceleration. An object's acceleration. Let's see. Other things. More takeaways of this. If I wanted to calculate force in here, I would have to supplement. I couldn't use just the work energy formula. Calculating the tension in the cord, we would have to consider forces. In the cord requires, that's a really bad written chord, requires supplementing work energy with Newton's second law. So we could find the velocity and then apply the equation for tangential acceleration, etc., etc. Tangential force, supplementing with Newton's second law. Second law. In fact, let's do that. Let's see what that would look like. Let me draw a free body diagram of the object at point as it passes through point 2. So I'm going to do the same thing I did in the previous chapter, and I'm going to draw a free body diagram and a kinetic diagram, or an inertial forces diagram. So the free body diagram would have this here. I would have weight pulling down, and I would have the tension P pulling upward. And then this would be equivalent to the M A tangential and M A centripetal or M A normal. M times the normal vector, or the normal, or the tangential vector, or sorry, or the centripetal vector, not tangential, sorry. Okay. Then I could go on further and say, so here, if I did a balance of these, summation of forces in the n direction, or in the normal direction, is M A n, or P minus W equals the same kind of thing we had previously. Well, let's see. If I replaced this with maybe W over G, so times V2 squared over L, because I know the I know that there M is going to be this here. This V2 squared over L is coming from the centripetal acceleration being equal to the velocity squared over the radius. We saw that now. What we saw previously was AN equals V tangential over rho or something like that. It's the tangential velocity divided by V2 squared over rho. But I'm just using the appropriate variables from our example here. Or I could also say here, the actual tension would be equal to be the weight plus W over G times 2GL over L here. And this here, this 2GL over L, well, let's see, this is coming from, let's see, where is this coming from? The W over G and V2 squared. Oh yes, this is something, sorry about that. Where that's coming from is simply plugging in our equation for V2 equals the square root of 2GL. So if I got this from the energy methods we saw previously, if I plug this in to V2, I get 2GL here, the square root cancels out from the square, and then things start collapsing fairly quickly. I'm going to get some maybe orange here to cancel things out. L and L goes away, G and G goes away, and I get simply 3W, or I get W plus 2W, or simply P equals 3W. So if I release a pendulum from a horizontal position, if I release the pendulum from a horizontal position, then it will generate 3 times, it will have a peak tension of 3 times the weight. Some of that is going to hold up, some of that tension is going to resist gravity at the bottom, and some of it is going to going into changing the direction of motion. All right, so now maybe I'll talk about one final topic for this evening before I definitely will need a part 3 for this lecture, but I think I may record that on another day, maybe even a part 4. This stuff we have a lot to get through in this chapter. So I might cover one more topic this evening because it's getting late. Okay, so I would like to talk a bit about power and efficiency, and I'll save some more numerical examples for later. So power and efficiency. Power and efficiency. Well, so what is power? Well, you probably remember this from even high school physics, but power is the rate at which work is done. The rate at which work is done. So the rate at which work is done, or I could simply say this is equal to du dt, d capital U, we're not talking integration by parts here, d capital U dt, or equals to f times dr times the dr vector and dt, or dr dt. Oh, I know what that is. That's F dot V. Oh, dRdt is velocity. So we can see that power equals the dot product at power at a point anyway, at a given instant, is equal to the dot product of force and velocity. And the dimensions, let's look at dimensions like I like to, as we always do. This is going to be 1 watt. You've probably heard this before, or just capital W. 1 watt is 1 joule per second, or 1 Newton meter per second. And then for English units, we will use 1 horsepower, or which is equal to 550 foot-pounds per second. Foot-pounds per second, which is equal to 746 watts. And please make sure you are familiar with working through all of these units. Now, I also want to outline something called efficiency, and we'll use the Greek letter nu. The Greek letter nu. So I'll try to write, this is nice kind of curly nu. This is efficiency. And we could define this 2 ways, either for work or power. Work would be something like a machine efficiency. This would be output work. Actually, no, wait, that would not work. Sorry. That would be, I'm thinking mechanical advantage. There the work is the same. You're not going to have a change in work. Sorry about that. But you can still have mechanical linkages that actually lose work through them. They're losing some of that work to heat. Output work over input work. Or, so that would be one way to use nu. Or, and I don't want to say these are equal. They're definitely not equal depending on the context. But I could also say nu equals power output over power input. Power output divided by power input. Power input. Here. All right. So I think that finishes the introduction for most of the material in work and energy. But after that, I just have a lot of example problems I want to work through to sort of give us some idea of how to apply this to various types and sorts of problems. So I think I'm going to, we will eventually have to cover potential energy as well, but I think I'm going to leave it at that for the evening. So thank you for watching. There will be a part 3 and maybe even a part 4 of this lecture. So maybe recording is a bit shorter blocks than I do when I'm in class, but hopefully that illuminates a few topics or a few items today. So thank you for watching, and as always, thank you.